Hi, I'm Paul. We're doing Leetcode must know interview questions. Today's challenge, binary tree, right side view. This is a medium challenge, and it says, given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes that you can see, ordered from top to bottom. Now, unfortunately, they don't really give a, a very good example of it here, because it looks like all you need to do is just traverse the right side of the tree and you have it. That's not really the case. I mean, well, for example, you might imagine that there was another node, a child node of 5, and we'll call that 6. Now, 6 would be visible if you were standing on the right side there. Again, you could take the 4 node off and maybe just put it over here as the left child of 2, and then 5 is the right child of 4. You would be able to see the 4 and 5 even though they were on the the left half of the tree. So there is more to this than just traversing through every right pointer on the tree. So this is listed under the breadth first search, like binary tree BFS, breadth first search category. You could do it. You could do it recursively. Showing the right hand nodes of each subtree. You would do it with the right subtree first and then the left subtree for each node. But really, the common way of doing a breadth first search is using a queue. So we did a number of depth first search tree problems, and normally for depth first search problems you use a stack, but for breadth first search you use a queue. So we're going to use a queue. We are going to put 1 in the queue, and that gets things started. At each point we know how many nodes are in each level. So if we put the 1 in, we know we got 1 node at that level. And at each level, we're going to do a loop for each level. We're going to loop through the number of nodes at each level, and when we get to the last node at that level, we're going to how do they want the output here? Oh, in a list. Okay. We're gonna add the rightmost node to the list that we return. So 1 comes out, and then we add 2 and 3 to the queue, and we set the level to 2. 2 comes out, and we add 5 to the queue. Now we don't adjust the level count. It's still 2. So then we take the next node off. This is the second node of 2, and so that goes in the answer. And we add this node to the queue, and now we adjust the level to 2. And we've got 2 nodes left. The 5 comes off, the 4, and we save the 4. Okay, let's see what an implementation looks like. Is it possible here that, well, let me look at the constraints. Oh, okay. The number of nodes in the tree is in the range 0 to 100. So it is possible to get a null pointer as input. So let's first define our, we're going to have a list of, they want a list of integers, right? Not a list of nodes. The values of the nodes. Okay. Okay, so we're going to have a list of integers. Call it result equals, it's not quite right. Result equals new array list. Okay. Oh, wait a second. Now, what do we want to return here? Oh, okay. So actually, yeah, if the root is null, they want, I assume they want an empty list. Well, that's what we're going to give them, and if it turned out to be wrong, we'll adjust it. Then we'll do this: if root equals null, return result. All right, so that takes care of the edge case. Now we need a queue. So let's define a queue. Java has a queue as part of the language, but it's an interface. So we can't instantiate a queue, but there are classes that implement the queue interface. That's not node, it's tree node. There are, and we'll call this queue equals, many people feel that a linked list is the best Java implementation of the queue interface, so we can use that. And then the first thing we do to get things started is to add the root node. All right. Now, as with any breadth first search, you know that you're done when the queue is empty. So we're going to loop as long as the queue is not empty. And the first thing we're going to do is get the size of each level. When I say the size, I mean how many nodes are in this horizontal level. All right, so int level size equals the queue size. First time through, that is going to be 1. All right, queue size. And then we're going to do a loop for each level, a for loop for each level. Where we say for int I equals 0, I is less than level size, I plus plus. If we are at the last node in the level. So if I equals level size minus 1, we are going to add, wait. Okay, hold on. That's not going to work. Sorry. First thing we got to do is dequeue the first node. So let's do that. Tree node. What do I want to call this? Tree node. Oh, let's just call it node. Tree node equals q dot poll. Poll is not like a peek. It's it actually removes the node from the queue. So, all right, so we have a node, we'll say result add, and then node dot, I think it's called val. Should know this by now. Yes, val, node dot val. All right. Having done that, we enqueue the child nodes of the current node, starting with the left. I will say if node dot left is not equal to null, then q dot add node dot left. Okay, and this will be very similar, but we'll say if node dot right is not equal to null, then we'll encode node dot right. Okay, so what is going to happen here? So the first time through, we take the 1 off, and 1 is going to be added to the result. All right, we're also going to enqueue 2 and 3. Wait. Level size. Okay, 1. Yeah, we're going to enqueue 2 and 3. Okay, and then we are going back to the top of the while loop. We're going to set the level size again. Level size is now going to be 2 because we got 2 nodes in the queue, 2 and 3. And then we're going to drop into the for loop. We're going to go through the for loop twice. All right, first time through, I is not equal to level size minus 1. So we don't add to the result, but we take node 2, which we just dequeued. It doesn't have a left child, but it does have a right child. That's the 5. So we enqueue it. So now what do we have in the queue? We have 3, we have 5. But because we're still in the for loop, we are not going to change the level size. It's still 2. And this is the second trip through the for loop. So dequeue the node. We are going to dequeue the 3. I does now equal level size minus 1. And so we're going to add the 3 to the result. Okay, and the final level will respond in the same way. Once we've gotten through this while loop, and the queue is empty, we are going to return the list. Okay, let's give that a try. Run. Compile error. Forgot a semicolon on line 35. Okay. All right, try it again. All right. Accepted. Yeah, I mean, this is really on the low end of medium, because it's just a classic breadth first search. To implement a breadth first search, you use a queue, and it almost like just works by itself. You just put the root in the queue, and then you take the root out of the queue, and you put the children of the root in the queue, and you keep taking things out of the queue and putting their children into the queue until you have processed the whole tree, and you wind up with a breadth first search. The only addition to the breadth first search is that we keep track of level size so that we can get the rightmost node at each level. So that's it. Oops, you know what? I probably shouldn't say that so soon before I submit it, but I feel good about it. All right, runtime 1 millisecond. Yeah, okay. Um, so that is the solution for binary tree right side view. I hope you enjoyed it. Please feel free to like, subscribe, comment, and see you next time.